So we were looking at the wave packet. We saw that a realistic wave function of a free particle, it should not be either a plane wave or a delta function. It should be somewhere in between and more correctly represented through a wave packet, which is a combination of several waves of different wave numbers or wavelengths, you can say. Okay. So the question is, I have the electron or a tiny particle as a wave packet. Now what happens if I make, say, a position measurement? If I try to measure the position of a particle, what happens? We'll try to see that. So if you try to measure the position of a particle, what you will get is the actual particle. It's not that, see, particle is spread out in reality, but when you make the measurement, you won't see the particle as spread out. You will actually get the particle. You will actually see the particle will be found at some position. Okay. So what happens in quantum mechanics, whenever you perform a measurement, the act of measurement, it disturbs the state of the particle. So the original state of the particle is a wave packet represented by a psi. But when you make the measurement, that act of measurement is going to disturb the state of the particle and the wave function is going to collapse. That's how they say in quantum mechanics. The wave function or the original state of the particle that collapses to one of the positions when you make the position measurements. So it's going to be like this. So you have this wave function, say this is the real part, and position of the particle can be between, minus infinity to infinity, and it's mainly located between x1 and x2. But if you make a position measurement, the particle will only be found at 1x and most likely between x1 and x2. Okay, so it will be found at one position. So what happens when you do the measurement? Something like this happens. If it is found at one position, so what's the state function of a particle at one position? It's a delta function. So when you do the measurement, the act of measurement is going to collapse this this wave packet into one of the position states. So what is the position state? Position state is a delta function. So it can be at x0, it can be, a peak like here, a peak like here, it can be anywhere. But most likely, it will be between x1 and x2 because the probability density of the particle just before the measurement, it's high between these points. Okay? And at the other positions, it's low. So you keep making measurements, what you will find, you will always find this delta function, but at different positions. So exactly the same set of measurement, the same equipment you use, the same thing, everything is same. You are making the measurement, but you are getting different answers. And that's what the probability is. So that's what the statistical nature of the quantum mechanics is. You won't get the same answer for the same exact set of measurement. It's not that your measurement is wrong. Okay, don't confuse it that, oh, there is some error in the measurement equipment. Even if your measurement equipment is 100% correct, even then you will get some kind of error in the measurement. By error, I mean you will get a different answer. Sometimes it's x1, x2, sometimes it's in between that, most likely between x1 and x2. So this is the nature of quantum mechanics. Similarly, you can make, momentum measurement. So you will get similar things. So this is, for example, let's prepare an ensemble of n particles. Ensemble of n particles exactly in the same state, psi. So all of them are in the psi state, and then you perform identical position measurements on all of these particles, right? So what will happen? Something like this will happen, as I just told you. Okay, all of them are in the same state initially. 1, 2, 3, 4, n. So this is ensemble of n particles. But you are making identical measurements on each of them and you are getting different answers. Okay. So this is uncertainty. Similarly, if you make a position this momentum measurement on again an ensemble of n particles, all of them are say in the same state psi again, and you make a momentum measurement. So what happens? It's going to collapse the wave function to a one particular momentum state. Now, how does a momentum state look like? How does a pure momentum state look like? Pure momentum state means P is very well defined. Right? Momentum has to be well defined. To be called it as a momentum state, the momentum has to be well defined. And when is the momentum well defined? When it has a definite lambda. So P is equals to h by lambda, right? So if lambda is very well defined, your P is very well defined. P is equals to h by lambda. You are using the de Broglie relation. So if I'm making a momentum measurement, so what happens? This wave function is going to collapse to a momentum state. And how does a momentum state look like? It will be either a sine function, cosine function, or e to the power iota kx, right? If you look at its real part or imaginary part, they will look like oscillating waves, because only the cosine and sine functions have the well-defined wavelengths, right? Only the sinusoidal functions, okay? Or e to the power iota kx, which is a combination of the two, right? Cos kx plus iota sine kx, I mean, it's just a combination. So this is what will happen. Particle 1, 2, 3, n, all of them are in the same state, but you keep making identical measurement, you keep getting waves, but of different wavelengths. Wavelength means different momentum. So there is an uncertainty in momentum also. It will collapse to a momentum state, well-defined momentum state, but what that momentum will be, that will be uncertain. Every time you make a measurement, I mean on a different particle, you get a different value of the momentum. Again, there will be a range of momentum which will have high probability, right? There will be a high probability of the particle to have a set of range of momentum, say from P1 to P2, as was the case in position measurements, right? Between x1 to x2, the probability was high. So there can be this range in which the momentum probability is high, P1 to P2. So chances are you keep making measurements and you are getting some number in between this range every time. Sometimes outside this range also, but most likely in this range. So these wavelengths will be different for different momentum, and that's how it's going to be. Okay, so actually this is a postulate of quantum mechanics. I'm going to be talking about eigenfunctions and eigenvalues shortly after covering this. So the postulate of quantum mechanics is that whenever you make a measurement, so the wave function, the actual state, collapses to one of the eigenfunctions. Okay, and whose eigenfunctions? Okay, so there is something called operator in quantum mechanics. So actually when you make a measurement, so it's kind of you are operating on the state of the particle, and that is going to lead to one of the eigenfunctions. We'll talk about it, but this is just a special case of that. So I made position measurement, I made momentum measurement, just two special cases, but this is in general true. You make a measurement, the wave function collapses to one of the eigenfunction of the measurement operator. Okay, so we now know that there is some uncertainty in the position measurement, there is some uncertainty in the momentum measurement. Even if my apparatus is perfectly fine, it's perfectly correct, even then there is an uncertainty. So then let's now come to this principle, Heisenberg's uncertainty principle. So it says that if you have an ensemble of particles and you make these measurements of position or say momentum, So there will always be some uncertainty, and there is some restriction on the product of the uncertainty in the position and the uncertainty in the momentum. So let's see what it is. So let's say this sigma x is the uncertainty in the position. Now what exactly the sigma x is mathematically? Sometimes in books it's very vaguely defined, uncertainty in momentum. Sometimes it looks like it's some kind of uncertainty in the measurement. That's on top of the actual inherent uncertainty in the quantum mechanics. That's on top of that. It can be there, yes. I mean, your measurement in reality will not be perfect. So there will be that uncertainty, but even if that's perfect, there is this inherent uncertainty that will always be there. So say that is sigma x, and mathematically it denotes the standard deviation of the position measurements. So if you have, say, an ensemble of particles, you make measurements on that, every time you get a different answer, so of course there will be some standard deviation. You can calculate the mean. There will be a data set x1, x2, x3, and this data set will have a mean and it will have a standard deviation around the mean. So sigma x is that. And how do you mathematically calculate it? So under root of this mean of x square. So these brackets, angled brackets, they denote mean or average. So average of x square, right, minus square of the average. And then you take the under root. You might have seen this definition before in your probably statistics course or something in your previous classes. So that's how you calculate the standard deviation. And similarly, you can calculate the standard deviation of the momentum, which is the uncertainty in the momentum. This p square mean minus square of the mean, take the under root. This is the uncertainty in the momentum, and Heisenberg's uncertainty principle says that sigma x into sigma p must be greater than or equal to h bar by 2. This product can never be smaller than this. At least it will be h bar by 2. Okay, so if you try to make, say, uncertainty in the position smaller, uncertainty in the position, this momentum will increase. If you try to make this smaller, this will increase, because the product has to be at least greater than or equal to h bar by 2. Okay, so what does it say? It says that if, say, you have a particle whose state function is very confined, say like this, this thing is very, say, narrow. x1 and x2, which were, say, the boundaries, say x1 and x2 are very narrow. So you are being able to find the position of the particle between x1 and x2, and because x1 and x2 are close, so basically uncertainty in the position has now decreased. But that's going to lead to increased uncertainty in the momentum. It means whenever you will make the momentum measurement, you are going to get very different wavelengths. Every time you make a momentum measurement, you will see a very different wavelength of the this wave function. Okay. Similarly, you can say if I have a well-defined momentum and the momentum uncertainty is small, the uncertainty in the position will be very large. So you may probably get particle, between a large range. So x1 and x2, the gap between them will be very larger then. Okay. And you might have seen this again in your school classes or somewhere, in chemistry, uncertainty principle. But in reality, the mathematical form, the books write it as delta x times delta p. So delta x is actually sigma x, delta p is the sigma p. Okay, now because we know that quantum mechanics is uncertain, it's statistical, so we can't talk about one particular number. We will always talk in terms of mean, standard deviation. That's how we deal with the quantum mechanics. So next is expectation value and operators. Okay, so how do you calculate the mean of the position? We have done it in one of the examples we saw. How do you do it? Like this. So mean value of the position will be position times the probability, right? So this probability is like a weight factor. If you have, say, several positions, say, let me assume for simplicity, say they are discrete, x1, x2, x3, and so on, and every x has its own probability, which is mod psi square. So you are doing x1 mod psi square 1 plus x2 mod psi square 2 and so on. But when you talk about a continuous set of available positions, they are not discrete. In general, they can be continuous. In case of a free particle, it can be continuous. Free particle can be found at any position, not discrete position. So it will be x into probability mod psi square dx, and instead of summation you integrate from minus infinity to infinity. So you get the mean position. This thing I can also write it as this, psi star into psi. That's basically mod psi square, right? Psi in general, it's a complex number. So psi star into psi is going to give you mod psi square. So that's what I have written, and I have embedded that x in between them. So psi star x psi dx. Okay, so let me just put it in this form, right? So you can write the mean position as this. Now let's try to look at the momentum. Okay, and then we will try to find the mean value of the momentum. So how do we define the momentum? So momentum is this, P equal to mass times velocity, right? But because we are talking about the means, let's take the mean on both sides. So what will be, mass is well defined. Mass of the electron is just the mass of electron. You don't have different values of the mass. So mass is very well defined, time is very well defined. So if I take mean on both sides, so I'm gonna get this, right? Yeah? Mean of the momentum is equals to m into d mean of x by dt. And let me put this thing here. Okay, so that derivative is just going to go inside this integration, right? So this is d by dt of this whole thing, and because it's an integration with respect to time, I can simply take it inside. So it will look like this. Okay. And now you can do some mathematical manipulation. It's there in the notes. I'm quickly going to go through it, but if you don't understand it, because I don't want to waste too much time on the maths, you can go through it. Quickly show you the steps, but we'll focus more on the final results. You can check the notes and maybe do the derivation yourself. So now I have this del mod psi square del t. So again, this will be written as this, right? So I can write this as psi star into psi, and then you can take the derivative, so you can write psi star into del psi by del t, chain rule. Okay, open the derivatives. Now what you have to find, you need to find out this thing and this thing. How do you find this out? Now use the Schrödinger equation. So from the Schrödinger equation, you know that del psi by del t is equals to this. Okay, this is basically the Schrödinger equation. So we used to write this, and this used to be on the right hand side. So I've just put the time on one side and the x on the other side. So that's how it will look. Similarly, if you take the complex on both sides, so you will get this del psi star del t. So this psi is going to become psi star. Iota will become minus iota. You taking its complex conjugate, and this will become psi star. Minus iota will become plus iota. Okay. Plug these back here, do some mathematical manipulation. You can go through this on your own. So there are of course second derivatives coming from this Schrödinger equation. Do some mathematical manipulation. What you eventually get is you will have to do a few more steps, integration by parts. I'm not going to go through it. You can go on your own. eventually what you will see after doing some mathematical manipulation, go through the steps. So you will see that this mean value of the momentum, it's an integral over psi star this thing psi dx. Okay, so basically it is psi star into minus iota h del psi by del x, and instead of writing del psi by del x, I wrote it like this intentionally. So that's what the mean value of the momentum will be. So it involves some kind of a derivative inside the integration. Okay, now you have now seen mean value of the position, which looks like this, and similarly the mean value of the momentum also it looks like it's in the same form, psi star into something psi dx. Okay, so this thing, the notation of this, a compact notation of this can also be this. So when I'm writing this is called ket. Okay, so there is a notation called bracket notation. So this is bra and this is ket. So when I write this psi x psi like this, so what I mean is basically this. So I'm going to embed x between them and take psi star psi and do the integration. This is also called dot product basically. So it's kind of a dot product in a mathematical sense. So basically you're doing the dot product of this and this, but it's fine. We are not going to go into that. Okay, so you can write this thing as this. Similarly, the position, the momentum, you can write it like this: psi star, this psi. So this is actually again psi. You put a p in between and then psi. So if I write it like this, it means psi star. There is a corresponding thing here, right? I'm not writing p here. It is something else, but psi. So this thing, when I calculate, say, the mean position of any quantity, position or momentum, and I write it like minus infinity to infinity psi star something psi dx. So this thing is called operator. This is the operator. This is called momentum operator. This is called position operator. So position operator is basically simply x, but the momentum operator is minus iota h bar del by del x. Okay, so every quantity in quantum mechanics will have an associated operator with it. So you will see position operator, momentum operator, kinetic energy operator. Every quantity, every physical real quantity will have some operator associated with it. So what do I mean by operator? Operator, as the name suggests, is going to operate on your state and do something. It's going to produce some result. And if I'm doing, say, the momentum operator, so I am taking the derivative of the state function del psi by del x, and then I multiply that thing with minus iota h bar. That's what the operator is. It's going to change the state to something. Okay, so the operators we denote by these x hat or x cap. So operator corresponding to x will be x hat, and the operator corresponding to the momentum will be p hat or p cap minus iota h bar del by del x. Okay, so say this is the position mean value, this is the momentum mean value. If I want to get the mean value of any quantity, any physical quantity q, so what I will do, I need to know the operator of that quantity, operator associated with that quantity, and I can use the same procedure. So the mean value of any quantity q, it will be given by minus infinity to infinity psi star operator corresponding to the q psi dx, and I can denote it like this. Okay, now how do I find this q cap? We'll see. I'm going to give you some examples and you will be able to understand more clearly. So as I said, this is a bracket notation. Okay. So basically you are putting this thing in a bracket, so a bracket notation. So left side is, sorry, I think I said it wrong. So left one, this one is bra and this is cat. And if I say do not write the q in between, if I simply write psi1, psi2 in this bracket notation, so what does that mean? It is basically minus infinity to infinity psi1x. You take the complex conjugate of the first, multiply with the second, integrate over the whole thing. So if I sometimes if I write something like this, so the meaning of that will be this. You are basically integrating, taking the complex conjugate of the first, multiply with the second, integrate over x. So it's basically the same thing. So you take the conjugate of this, so that is psi star, and this whole thing you can assume that this is, so this is psi1, and this whole thing you can say it is psi2. So you take the complex conjugate here, and this whole thing is psi2. So this is here, and you integrate with respect to x. Now let's try to calculate some operators. Let's talk about energy operators. So we have seen the position, the momentum, but I know the form of the momentum operator and the position operator, but can I calculate kinetic energy operator, or say potential energy operator, or total energy operator, or for any, any operator for that matter? So how do we define the kinetic energy? So first step is that you write down the classical relation or the classical expression of that quantity. So what is the classical expression of the kinetic energy in terms of, say, momentum? Sorry? Half mv square or p square over 2m. P is the momentum. So kinetic energy is, let me denote it by t equal to p square over 2m. So if you want to calculate the corresponding operator, what you have to do, you simply have to replace the momentum or the position with its corresponding operator. So how I can write it like, so t cap, it will be equal to 1 by 2m. I can write it as p into p, and let me replace that p with its corresponding operator. So p cap into p cap. Okay? And what is this p cap and what is this p cap? So this p cap is this minus iota h bar del by del x, and again this thing, multiply, so this will be the operator. Iota square minus 1 minus minus plus, there is a minus here. So h bar square by 2m del square by del x square. Similarly, I can evaluate the potential energy operator. So potential energy, it does not have a form like p square by 2m or anything like that. So but potential energy usually will be in the form of some position. So potential energy will be a function of position. For example, the potential energy between two electrostatic charges, it's a function of position, 1 by r dependency, q1 q2 by r proportional to q1 q2 by r, potential energy between two charges. So it's a function of position usually. If you talk about, say, the potential energy of a spring, although you will have to take a very tiny spring or some atomic version of that. It's like, say, you have two atoms and there is some kind of a force between them, so that you can model that as some kind of a spring force. So that is again going to be in terms of position, half k x square, where k is the spring constant, if you remember. So usually the potential energy will be a function of x. So how do I calculate the corresponding operator? Say if I have half k x square, k is spring constant, not the wave number. So this is my classical relation. So how do I calculate the operator? So for operator, I am simply going to replace this with its operator version. So half k into x cap, but x cap is actually x. So it is simply half k x square again. Okay. In general, you will have v as a function of x. It will be some function of x, but you are simply going to replace that x with x. So it remains the same. So position, this potential energy operator is actually the your classical potential energy as you write. So this V cap is simply V as a function of x. Now what will be the total energy operator, which is called Hamiltonian, denoted by H cap. H cap will be calculated from the expression of H. H is the total energy. What will be the total energy? Kinetic energy plus potential energy. This H equal to T plus V. Its operator version will be H cap equal to T cap plus V cap, right? So T cap is this, V cap we know it's Vx, so H cap is this. This is Hamiltonian, or the energy operator, or total energy operator. Now this is an important quantity because this is what appears in the Schrödinger's equation. How? Let's write the Schrödinger equation. So Schrödinger equation is this thing. Iota h bar del psi by del t equal to minus h bar square by 2m del 2 psi by del x square plus Vx. If I take this psi out, it will look like this. I can simply take the psi out. What is this? H bar. Okay, so the compact form of Schrödinger equation is this. Minus iota h bar del psi by del t is equals to Hamiltonian acting on psi. So whenever I am applying an operator, so I am applying this operator to this state. So h bar acting on psi. Okay, now let's quickly talk about the eigenfunctions and eigenvalues. Again, an important concept. I will be again and again keep using these terms, eigenfunction, eigenvalue, when we talk about the band structure. So mathematically, I mean, eigenfunction is not, eigenvalue, eigenfunction is not a quantum mechanical concept, it's a mathematics concept. You might have seen the eigenvalues of a matrix, for example. Right, so it comes from the mathematics, but it has special, you can say, significance in quantum mechanics. So what is the eigenfunction and eigenvalue? So if I have an operator, say a cap, I'm talking about the eigenfunction and eigenvalue of this operator. So if I have an operator, given operator a cap, a function psi is called its eigenfunction if it satisfies this condition. If my operator acts on a wave function, say the wave function is phi, and that results in some constant, say constant is a, times that function again. So then this phi is called an eigenfunction of a cap. Not all the function will behave this way. So if I do a cap on, say, any random function, say psi, it may not give me constant times psi. Will not always give me. Only few special functions will be able to do that. And let me denote the set of all those functions by phi, and that set is called eigenfunction. Eigenfunctions or eigenfunction. If it is one, then eigenfunction. If it can be several also. Okay, so eigenfunctions. And this thing, this constant, it's called eigenvalue. This is eigenfunction, and corresponding eigenvalue is this, A. Now, as I said, there can be multiple eigenfunctions that satisfy that relationship, a cap into phi equal to some constant time phi. There can be several such functions. So it may be one eigenfunction or multiple eigenfunction. Okay. Similarly, it can be one eigenvalue or multiple eigenvalues. And further, these multiple eigenvalues or eigenvalues, they can be either discrete or they can be continuous. So it could be like I have a1, a2, a3, a4, multiple such discrete values, but I may also have a continuous eigenvalue, which takes all the real values. It does not behave like a1, a2, a3, so there is no gap. It can take any real value. So that's also possible. We will encounter cases of both. So let's try to take an example. If I have to calculate the eigenfunctions of, say, momentum operator, let's try to do that. So how do I start? I start with this statement. So momentum operator, if phi p is an eigenfunction of that, it has to satisfy this relationship. Now please replace this p cap with its corresponding operator form. So what will I get? I will get this. So p cap is minus iota h bar, d by dx phi p equal to, p is a constant corresponding to this phi p. So this, okay, p is the eigenvalue, phi p is the eigenfunction, and satisfy this relationship. Now can I evaluate what will be my phi p? Can you solve this differential equation? It's a first order differential equation, very easy to solve. So what you can do, d phi p, you can take this at the bottom, dx, integrate. What do you get? Get this, take here, integrate both sides. P is a constant, so it's not a function of x. You can take it out. This will be the log of phi p, right? Log of phi p, and log of phi p will be minus iota divided by h bar p into x. And you can take this exponential on both sides. So here it will be phi p, and that will be exponential of this, e to the power iota p x by h bar. There is some extra sign or something. Yeah, I think this is extra. Should be plus. So you get this phi p equal to a e to the power iota p x by h bar. Let me denote this p by h bar with a quantity k. Why I am denoting it with k? Look at the form of this function. So we have seen this. Yes? Didn't we see this initially? So this is a wave function which has well-defined momentum. We saw this, but we were just trying to make it without exact mathematical formulation. We just tried to find out a function which fits our intuitive understanding. So intuitive understanding said that, okay, it's a momentum wave function, it should have a well-defined wavelength, so it should look like e to the power iota kx. What I'm getting is the same thing, e to the power iota p by h bar, let me write it as some k, e to the power iota kx. So the functions that we were talking about actually were the eigenfunctions of the momentum. So eigenfunction, if you want to intuitively understand, so it's a function, it's a state in which that particular quantity is well defined. So if I'm talking about momentum eigenfunction, so I'm talking about a state in which the momentum is well defined. If I'm talking about, say, a position eigenfunction, so I'm talking about a state in which the position is well defined. Talking about an energy eigenfunction, energy is well defined. Okay? So only these states have well defined physical quantities. Only that physical quantity. Say I have a momentum eigenstate. So it has a well defined momentum, but only the well defined momentum. Okay, if you say, does it have a well defined energy? No. Does it have a well defined position? No. Position will be highly undefined because sigma x into sigma p is greater than or equal to h bar by 2, Heisenberg uncertainty principle. If I have a well defined momentum, uncertainty in the position will be huge. So completely undefined position. So these things have well defined quantities, that particular quantity for which you are calculating the eigenfunction. So now, can I say that whenever I'm making a measurement of a physical quantity, my wave function is going to collapse to one of the eigenfunctions? When I make a momentum measurement, what did I see? I get waves of different wavelengths. Well-defined waves. So what are well-defined waves? Eigenfunctions of the momentum. So whenever I make a measurement, I get one of the eigenfunctions. It can be any eigenfunction because it's probabilistic, statistical. Some of the eigenfunctions will have higher probability, some of the eigenfunctions will have lower probability. So it depends. Okay? P is some real number. There is no restriction on P as such. So what will the P be? Is it discrete or is it continuous? It's a continuous. I mean, P can be any real value. It can be negative, positive, whatever. Momentum is a vector quantity. It can also attain negative values. So this is just I was talking about, right? So it's going to collapse to one of the eigenfunction, and that will have a definite momentum eigenvalue. Similarly, we can make similar conclusions for the position, but we saw that position eigenfunction looks like a delta function, right? But can we mathematically find it using the same procedure? Let's see. So for the eigenfunctions of the position operator, x cap into phi x. So phi x will be the position eigenfunction, must give me some constant, say x naught times phi x. Right? Now let's see which functions can satisfy this thing. I have to find out this thing, right? In x cap I know it's some x basically. So let's try our delta function. Okay, let's see if it satisfies this relation or not. Dirac delta function. So what was my Dirac delta function? It was some delta of x minus x naught. It was some kind of a peak somewhere at x equal to x naught. This is my so-called position state. I mean, intuitively I found out. I'm just checking whether it satisfies this thing or not. So let me do x cap into, it can be some, say the amplitude is some a. So instead of writing delta of x minus x naught, I can in general write some constant times this thing. So x cap into a delta of x minus x naught must give me, okay, so this thing will come later. So x cap will become x here. This is the same thing. Okay, now let me try to find this thing out. So x cap, when it acts on this function, it will simply multiply this x with this thing. So how will this function look like graphically? Let's see. So graphically I have two functions. So one is simply x and one is this delta of x minus x naught. So delta of x minus x naught is this thing, right? So this is say y1 and you're multiplying that thing with x. So y equal to x. So what will be the y equal to x function? This straight line. So you're multiplying these two functions basically, correct? So y1 times y2. So y1 is this x, this function, and then you have this function. If you multiply these two, what will you get? This is 0 everywhere except at x equal to x naught. Okay, so what it is going to do, it's simply going to be non-zero at x equal to x naught. So this x times this will become x naught, simply x naught into a. That's it. Do you get my point? This will be 0, this will be 0, but at x equal to x naught, it is non-zero. Okay? So only at that point I get the product a into x naught. That's the only thing I get. And everywhere else I get 0. So it's basically kind of sampling this thing, sampling one point. Ax naught. So what do I get? Product of this into this is equals to Ax naught into delta of x minus x naught. What is this? Amplitude is now A into x naught. So Ax naught into, this is still a delta function at x equal to x naught. So this is delta of x minus x naught. And what is it multiplied with? A times x naught. So x cap into this thing is giving me Ax naught or x naught A into delta of x minus x naught. It means this delta function A into delta of x minus x naught, this thing, it's phi xx eigenfunction. So again, whatever we saw in our previous class, delta of x minus x naught, that was actually an eigenfunction of the position. And it makes sense because I said for an eigenfunction that quantity must be well defined. Only for a delta function the position will be well defined, you know, because that delta function only peaks at one position. So it gives you infinite probability at that point. And at rest of the point, no probability. Makes sense. And whenever you are going to do a position measurement, that's why you always get one of the delta function, one of the eigenfunctions basically. So now let's talk about some special states. So we have talked about some special states already, which are eigenfunctions. A few more special states which are called stationary states. So these are special set of states whose probability does not vary with time. So mod psi square will not be a function of time. That's why the name stationary. How do we obtain these states? So we start with the Schrödinger equation. There is some small mathematical derivation, not very difficult to understand. And I'm going to assume that this potential is only a function of x, it's not a function of time. It can in general be function of time, but the type of problems we will be doing, in those problems we will not be a function of time, at least the simplistic view I'm going to give you in this course, that in that we will be only a function of x. So I'm going to assume that it's independent of t. That's the first assumption. And let me, now I have to, evaluate this differential equation. It's the second order differential equation, and it also has time. Not only has x, but it also has time. So what I do, let me do this equation solving by the separation of variables. So it's a very it's a common method. People use it in electromagnetics also, right? So what you do, you write this psi as the product of two functions. One function will be completely a function of x, another function will be completely a function of time. So basically this psi x comma t equal to psi only a function of x. This is small psi, by the way, this is capital psi. So both of them are not same. It's only a function of x and it's only a function of time. Let me assume that solutions like these exist. If they won't exist, I won't be able to solve it, or I will get something weird in the end. If I don't get something weird in the end, it means I may have a set of solutions which are like this. So let me assume this. Okay, I can separate them. Let's try. I mean, that's how you solve the differential equations. Keep on trying different solutions. So let me try this one. Put it here. What do you get? You get this phi f here. And because now, see, this is only a function of x, I can take it out of the time derivative. And this is only a function of time, so I can take it out from the x derivative. Okay? And these are simply this is simply the product, so fine. So I get this equation. Okay? Now let me divide both sides with phi times f, sorry, psi times f. Divide both sides with psi times f. So what that will do, it will give me this. This is cancel. This will get cancelled, so you will get psi here and you simply get v here. Now look at this equation closely. In this equation, the left hand side, it's completely a function of time. You have the time derivative and f is a function of time. So left hand side, it's totally a function of time. Let's look at the right hand side. Right hand side is completely a function of x. You have derivatives with respect to x, and the psi, it's a function of x. And v is also a function of x. It's not a function of time. So if left hand side is a function of time, right hand side is a function of x, t and x are independent variables, when can this be possible? It can only be possible when this equal to some constant. Only then you can say that this can happen. Right? It has to be a constant because only the constant is independent of time and x both. Okay? So this and this must be equal to the same constant. This is a constant, this is a constant, and both of them are of course equal. So let me call that constant as E. Okay? Why E? I mean, look at the dimensions on the left hand side or right hand side. Get the dimensions of energy. Let me just write it as some E. Okay? So let me call it as E. Now, we'll solve both of them one by one. Okay? So the first one, only a function of x. This is equals to E. Let me multiply this psi on both sides. So what do I get? I get this equation. Minus h bar square by 2m del 2 psi by del x square plus v into psi equal to E psi. Okay. By the way, this thing is h. This is h cap psi equal to E psi. Right? This is also known as time independent Schrödinger equation. It's a time independent version of the Schrödinger equation. When you are saying time independent Schrödinger equation, basically you are solving only the psi of x, only that x part, not the time part. Now let's talk about the time part. So iota h bar 1 by f del f by del t equal to E. This is a very easy equation to solve. So you have df by f, and you can take the time here, integrate both sides. What do you get? What do you get? So df by f equal to E by iota h bar, right? So you take the integration, both sides. Oh, there is a dt here. So this will be some log of f equal to some et upon iota h bar. This is exponential, so exponential of some et by iota h bar. Or you can take this iota in the numerator. So 1 by iota is minus iota et over h bar. So that's what my f is. There will be some integration constant also c, but for simplicity you can assume c equal to 1. That will not create any difference, because eventually you are going to multiply psi x into f. So let me absorb the integration constant of f say into psi. So you can assume simply c equal to 1. So this is what you get. So what is my psi of x comma t? Psi of x comma t is the psi x, which is going to come from this equation. You will have to of course solve it, This is a double derivative equation. You need to solve this. You get this part, and this we have already solved. So we have this. So total function looks like this. Right. Now, what about the stationary part? Yeah. Can you tell me now what will happen to mod psi square? Mod psi square, if you take, what will happen to this? This is a complex number, e to the power minus iota et over h bar. Right? The magnitude of this is what? What's the magnitude of e to the power iota theta? This is 1, always. So e to the power iota anything, if you take the mod of that, so that will be mod of psi into mod of this e to the power iota something something, and this is going to be 1. So this is simply mod psi. Okay, mod psi square will be then what? Or you can also do, mod psi square is equals to, psi star into psi. So psi star, if you take conjugate of this, so this will become plus, multiply, so this will become, psi square, and this exponential plus and minus will cancel. Now, do you see now this is mod psi square of the total function, which is x comma t, and what is on the right hand side? It is only a function of x. It means the total state function's probability density, it is independent of time. It's only a function of x. So such states are called stationary states, and such states will have variable separable solution. You can independently write psi into the time part, simply the multiplication of the two. Okay, not only that, any physical quantity, the mean value of that physical quantity in the state psi, that will also be independent of time. Okay, mean value is also known as expectation value in the quantum mechanics. So expectation value or the mean value or the average value, same thing. How? Expectation value of the physical quantity, any physical quantity, say q, and the state of the system is say psi, the mean value of that or expectation value of that will also be independent of time. So how do I calculate the expectation value of any quantity q in the state psi? So what do I do? This psi star q cap psi, that's the mean value, right? So you plug psi star and psi here. So what is psi star? Psi, the star of this and plus here, this q cap and psi e to the power minus iota ut. Okay? And this, they're going to cancel each other. What do you get? You get this. Is it a function of time? No. Everything is a function of x here. Okay? So mean value is also independent of time. Say the mean value of energy, it won't change with time in this state. Or the mean value of momentum, or the mean value of anything else. Okay, now let's focus more on this part again. So I told you that this is called time independent Schrödinger equation. There's no time here. And this is the main part we need to solve. When we solve the Schrödinger equation and we are only looking for stationary states, so this is the main part, that is the difficult part. The time part we have already taken care of, so that is simply e to the power minus iota et over h bar. We already know that. If you calculate the psi from here, you need to just multiply the two to get the solution of the total Schrödinger equation. So this is the compact form of that. And what is this psi? What is this psi? Because h bar acts on this psi, and that gives me some constant. E is a constant, right? Times psi. So this psi will be nothing but the eigenfunction of the total energy. Yes? H cap psi gives me constant times psi. So what is psi? Psi is an eigenfunction of the Hamiltonian. So when you say you are solving time independent Schrödinger equation, basically you are trying to find the eigenfunctions of the Hamiltonian operator. That's what you are doing. And as we know that there can be more than one eigenfunction, psi1, psi2, psi3, and there can be corresponding eigenvalues E1, E2, E3. E1, E2, E3, they can be in the discrete form, or it can be continuous also. Both are possible. So any differential equation, when you solve, there is something called a particular solution, and then there is a general solution. So particular solution is one of the solution that satisfies my differential equation, but there can be many. So what will be the most general form of that solution? Let's see. So let's talk about the general solution of the Schrödinger equation, and it's important. It's important to understand a few things later on. Okay, so we know that we can have different wave functions solutions, because I can have say this psi1. So psi1 and E1 I get from the time independent Schrödinger equation, but can be more, psi2 E2, psi3 E3, and so on. Okay, I'm just keeping it discrete just to understand the concept, and then we will make it continuous also. We'll write that form also, but let's assume that say E1, E2, E3, they are some discrete eigen energies or eigenvalues, and corresponding eigenfunctions are psi1, psi2, psi3, and so on. So how do you find out the total this wave function which satisfies the Schrödinger equation? So corresponding to this psi1, small psi1, I will have this capital psi1 equal to small psi1 times that time independent, that time dependent part. So that will be e to the power minus iota et over h bar. What is e in this case? E1. So this. Similarly, I can find the total psi corresponding to this psi2. That's also allowed, right? That will also satisfy my differential equation, the Schrödinger equation. So psi2 into e to the power minus iota et over h bar. Similarly, corresponding to psi3, I can write another psi, capital psi3. I can write several psis, psi1, psi2, psi3, corresponding to different solutions of the time independent Schrödinger equation. Because small psis can be several, so I can have several capital psis as well. But what will be the most general solution that satisfy my Schrödinger equation? Each one of them separately satisfies the Schrödinger equation. Okay. So this, if I put psi1, psi2, psi3 here, left hand side will always be equal to right hand side. So they will satisfy. But they are all particular solutions. What is the most general solution you can write? The form of the Schrödinger equation is such that if psi1 is the solution and psi2 is the solution, so will be psi1 plus psi2. You can check. Actually, the form of the Schrödinger equation is such that if it satisfies psi1 and psi2, it will also satisfy psi1 plus psi2. Let me show it. Yeah. Now let me add these two. What do I get? This I know it satisfies, so it means this psi2 also satisfies. So this. So let me add both of them. So that will become del psi by del t, psi1 plus psi2, and h cap psi1 plus psi2. Right. Equation number 1, 2. If you add 1 and 2, you get this. And psi1 plus psi2 is psi. So it means if psi1 and psi2 satisfy the Schrödinger equation, psi will also satisfy the Schrödinger equation because it's the sum of the two, psi1 plus psi2. So because of this nature of the Schrödinger equation, you can always, if you know one solution, psi1 another solution, so algebraic sum of them will also be the solution. But this is not just limited to psi1 plus psi2. It can be psi1 plus psi2 plus psi3 also. In fact, it can be a1 psi1 plus some a2 psi2 also. You can even take some products. Okay, what will be the most generic solution then? So we know that if psi1 and psi2 are solution, C1 psi1 plus C2 psi2 will also be the solution. C1 and C2 are some constants. In general, this will also be the solution. What is this? This is basically C1 psi1 plus C2 psi2 plus C3 psi3 and so on, plus Cn psi n. And each individual psi can be represented as this. So psi1 will, for example, be what? Small psi1 into e to the power, minus iota e1 t by h bar. So that's what it is. So in general, for psi n, right? Any generic term can be written as psi n. So psi nx e to the power minus iota ent over h bar. And what will be the coefficient? Coefficient is Cn. Integration over n equal to 1 to infinity. Got it? It's basically simply the summation. Just a compact form of writing the summation. So this is the most generic solution of the Schrödinger equation. What will be the value of this psi at t equal to 0? So simply this, if I put time t equal to 0, so this term is going to become equal to 1. Right, so psi x comma 0 is simply Cn into psi n. So it's simply a linear combination of the eigenfunctions of the energy, at least at time t equal to 0. Okay. The total solution is simply algebraic sum of the eigenfunctions. Whose eigenfunction? Energy's eigenfunctions. Yeah, this is eigenfunction of energy. You know that. So this is when my E1, E2, E3, E4, they were all discrete. What if I have a continuous energy? So this integration is going to convert into, this summation is going to convert into integration. Okay. So for a continuous eigenvalues, we will have to use a continuous index. So here I am using a discrete index, n equal to 1, 2, 3, 4, something. So I will have to use a continuous index, and corresponding to this thing, I have psi x comma L. So here I had psi n. N was the discrete index. The L here denotes the continuous index. It will be a function of psi will be a function of that. And corresponding to this, I have this. E is a function of n here, but here it's a function of L. And I have replaced this Cn with some Cl, a function of L times dl, and you integrate. Okay, because when you have a continuous set of wave functions, each of the coefficient will be actually very small. So this Cn is replaced with C into dl, and you keep on adding many such wave functions, and you get the integration. Any confusion in this? So I have simply converted the summation into integration. Okay.